Hello, I'm Stella Malapaki, and I'm a PhD candidate at the Norwegian University of Science and Technology. I will present to you our work on querying the top K-dominant traffic flows on large urban road networks, done together with Paolo Sotovia and Stefano Bortoli. Before we begin, I would like to introduce you to what is a traffic flow. Practically, it is a sequence of road edges that are traversed by multiple cars. For example, in this picture taken from Google Maps, the green, orange, and red roads show some traffic flows on these roads. The ones that are more frequent are the dominant flows. So why do we need to identify the dominant flows? Dominant flows can potentially create traffic jams. Having less traffic jams can increase the mobility inside cities, help the fuel waste and air pollution problems, and in general make people less annoyed while commuting. Dominant flows are an important aspect in traffic optimization techniques that can give useful information on analyzing the traffic dynamics in cities and help traffic authorities. Since dominant flows are created by humans, they are dynamic and changing through time. Different roads are part of a dominant flow in the morning when people are going to work, different during the afternoon when people are returning, and different during the night. Also, multiple dominant flows during the same time of the day can overlap each other, as for example, in intersection F, the pink and the orange flows, or even constrain each other, as for example, in intersection D, the blue and the pink flows. So it is important to know which are the dominant flows to help improve the traffic optimization techniques and the traffic authorities. During this work, our case study was an area in one Chinese metropolis where cameras were placed on road intersections, monitoring the traffic. However, this real-life data created the bigger challenge in this work. The detector cameras were not placed in all the intersections on the road network, which ended up in missing flows. Also, the cameras during their lifetime could suffer from various issues like malfunctions, dirt, bad weather conditions, which also created missing detections that ended up in missing flows. Another challenge was the great amount of data we needed to process. For 1 month, for example, we had 371 megabytes of detections. Last but not least, identifying the dominant flows is a problem related to the frequent pattern mining problem, which is not an easy problem. Our problem, as mentioned, can be related to the frequent pattern mining problem, which is not an easy problem and it's not a new problem. However, the previous works done were not intended for the traffic applications like the prefix span method, or if they were, they pose limitations regarding the real-life data that we had in our case as the PSSS method. Specifically, the PSSS method uses the successor list for each road edge to find and extend the frequent flows that in our case cannot be applied because, as mentioned earlier, we have missing detectors and sometimes missing detections. If applied, the resulted flows are wrong with respect to our definition. To describe our definition on the problem, we need first to define its components. So, a detection is a combination of a road edge, a timestamp, and a vehicle ID. A sequence of detections for a certain vehicle creates a trip. A flow is a sequence of road edges, and the period of time during a day is called a time window. We can define the length of a flow to be the number of road edges it has, and the frequency, how many vehicles are including this flow in their trips in a given time window. The score of a flow is a weighted combination of its frequency and its length. We discard the flows that have length and frequency less than a minimum. Finally, our problem definition is to retrieve the top K flows with the highest score. Our proposed method uses the IST index to store the vehicle trips. It consists of an inverted index which has as keys all the subflows with minimum length and values pointers to the suffix trees. The suffix trees are storing all the subflows with length longer than the minimum that are having keys as prefix. Each node of the suffix tree has also a pointer to a list of all the trip IDs that contain the subflow of the node. We use a supporting list of trip IDs, vehicle IDs, and start and ending timestamps for the trips to identify easier the trips inside the time window. The proposed method that reads the data from the IST index is called flow scan, and it is divided in 4 steps. First, it finds the trips inside the time window for the supporting list. Then, it identifies which keys from the IST index need to be traversed. The third step is to find all the flows that are longer and more frequent than the minimum length and frequency. The last step is to calculate the score for all the found flows and then return the K ones with the highest score. Note that our proposed data structure and method do not depend on the road network, and so they enable to overcome the limitations of the previous work with the successor list. In our experimental evaluation, we use 4 algorithms: the prefix span, the PSSS, the flow scan, and the naive. The naive is using the road network to store in each road edge the vehicle detections that happened. Each trip is connected with pointers from one detection to the next, so that we are able to follow the trips in case of missing values. The algorithms were evaluated based on their running times for building the supporting data structures and querying the dominant flows. We have experiments measuring the effects of various parameters on the running times, such as the number of the data for the scalability of the algorithms, the time windows on the query time, and so on. We use 4 datasets to compare the said methods. The RM is a real-life dataset collected in a period of a month from traffic detectors in an area of a Chinese city. The detectors were in 6 intersections, monitoring the traffic on 44 road edges. The RD dataset has the data for RM for 1 day of the month. The COMB and the GRID datasets are synthetic ones that were created to evaluate the scalability of our method and to be able to use the prefix scan and the PSSS method that, as mentioned, are not applicable for the real-life data. Some indicative results from the scalability experiments using the COMB data are shown here. Even if our proposed method is slower compared to the PSSS method for the synthetic and complete data, it is still usable and efficient in a real setting since it has small running time differences. In addition, our method flow scan can be applied to real-life data that, as mentioned, are incomplete in contrast to the PSSS method that will not produce the desired dominant flows. For more experimental results, please have a look at our paper. In conclusion, in this paper, we propose a method for identifying the top K dominant traffic flows on real-life urban road networks that can overcome the limitations of the previous works that were not able to handle the real-life data. Based on our experimental evaluation, we show that our proposed method is comparable to previous methods on synthetic and complete data, and in addition, it is scalable and efficient on real-life incomplete data. For more information, please refer to the paper or contact us. Thank you.